Nice. Okay.
And those of you just tuning in, welcome to Æther Roundtable number 23. Today we're going to be talking about, quite frankly, we're going to be examining how math became reality. And Alan is going to run through a presentation that he has given in the past, but as we learn more about these topics, there's always more to go into on these topics. So it's kind of a redux, and we'll be adding more. He'll be adding more context, more that we've learned. And also, I just thought that this topic is so crucial to this discussion that I thought it'd be a good time to go through it again. Essentially, it's going to go through all the quote-unquote relativity proofs. So let me go ahead and kick it over to you, Alan.
Yeah, thank you for that introduction. So this is going to be kicking off from the proofs of general relativity, right? Because this is an extension of the special theory. So as we begin here, we'll kind of touch on the special theory a little bit, and then we'll get into the proofs that are put forward of the general theory so that they could be, basically merged mathematically, right, through the equivalence principle. And we'll get into what all that means as we go through here. So this is quite a lot of information. So there's some prerequisites that we'll get into first. Let me see if I can hit the right button to go full screen. Cool. All right. So this is a comprehensive look at the historical and classic experimental evidence put forward for relativity theory by space audits.
Can you share it with Discord?
You know what? That'd be super dope. I knew I was forgetting something. All right, here we go. And then make sure that's 1080p. Get the good quality around here. Should be good. Okay, excellent. Cool. So here's all the contact information. All right. So first here we have the proofs of general relativity that they say, right? So they say that there's the perihelion precession, and that there's the deflection of light rays by the sun. More importantly, there's gravitational redshift. Now, the first two proofs are more calculative. They're actually postdictions, right? So we could, in order to bolster the proof of that, thank you for that. In order to bolster the proof of the theory, right? The prediction of the gravitational redshift is the most significant. So like we'll pay special attention to that proof because that's going to replace the ether as the mechanism for light to change its frequency or spectrum or anything like that, and it's going to enable them to say that spinning and warping of space-time is what facilitates that interaction while keeping the speed of light the same, right? Because in their model, the speed of light is the same. So anytime there's a change in the frequency, it's always proportional to or inversely proportional to the wavelength. So it just plays this a photon just plays this perpetual back and forth where it can maintain the same speed but change frequency and wavelength. Okay, so let's see. So those are the proofs put forward, and we're going to go over those meticulously, right? So here's Einstein writing to some publication in London about the proofs of his theory, and he says that these are the core elements of his theory. So we should definitely pay attention to the history of these so-called proofs, right? And in particular, the gravitational redshift, right? Because the deflection could be due to various factors, and the perihelion precession is a calculative postdiction, so it really doesn't mean anything. So the big key item here is the redshift, because that's going to be their mechanism is a calculative postdiction to cause a photon to alter its trajectory, right? Because if it's not interacting with the gravitational field or space-time curvature, then it's not able to frequency shift or anything like that. So another important aspect here, someone's hot micing. Another important aspect here is the idea of proper time and the time in the frame of acceleration or in motion, right? So we'll have the way that they represent this, like time dilation, because we're going to go through a lot of, like, a way that they try to mechanistically explain things is through the mechanism of time dilation, right, or length contraction. So this is what this looks like on a graph. If you were to take two observers, right? So in this example, this is for a rotating Sagnac device, so just a rotating interferometer. But this is the way you could look at it, right? You would have a stationary observer here, and then he's going to have an additional axis added to his XYZT axis, right? And that's going to be the T line. And they add that perpendicular to the X axis, right? So perpendicular to the direction of motion is always going to be the world line or the unity line, they'll sometimes call it. Okay. So what we're looking at here in the center of this graph, you can ignore all these lines going in different directions and all this stuff. Just pay attention to this center one with O right here. This one going up is proper time for the stationary observer, right? And then this line going diagonally is the divergence of time due to the motion of the other observer, right? So this other frame is in motion, right? This frame is stationary. This divergence in the time axis is represented by that hyperbolic divergence, right? And it's relative to the speed. So when they get into length contraction and time dilation and all this, this is how they're looking at it, right? This is what they're talking about. So time dilation exists in a graph, essentially, right? So here's Minkowski's spacetime contribution. So this graph is like a simplified version of Minkowski spacetime. So this looks hella confusing, but it's pretty simple, right? All it states is that geometrically speaking, as long as an event takes place in this side of the cone, that it will be automatically covariant under transformation, which is not the subject of this right now. But just to quickly kind of go over the abstraction of what they put forward, right? The representation, right? So again, we're looking at a stationary world line with a stationary distance, right? Your world line axis, your time axis, and your x-axis. And then we're looking at an observer in motion, and his velocity is going to change space-time proportional to that velocity. And keep in mind, this isn't for like Galilean velocity addition. This would be like for things moving at relativistic speed, so-called, right? So, and that's what causes the hyperbolic divergence from the proper time, right? From the stationary observer. All right. And then anything that happens outside of the light cone would be a violation of causality. It wouldn't work mathematically, blah, 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 right? So they kind of simplified it in that. And then this is what it looks like, in a simplified version. All right, cool. All right, so all of the measurements that they go over are pretty much done in arc seconds or arc minutes. So we'll get familiar with that. Oh, is there any questions on the time dilation or the divergence or anything like that? Is everything making sense so far? Anyone?
That seemed pretty good. That was a pretty good explanation.
All right, cool. Can I turn my mic up a bit? Maybe if I move closer, that'll help. Let me know. Let me know if that fixes it. I don't want to adjust the knobs right now, but if this fixes it, just let me know. Okay. So we'll get familiar with the measuring system here. So we got our protractor here, and if we look at the distance from 1 degree to 2 degrees, we can break that down into 60 arc minutes, right? So we could split that into 60 sections. So we could split 1 degree into 60 minutes, right? Oops. And then from there, we can break those minutes down into 60 seconds each as well. So we can break 1 degree down to 1/3600th of a degree, right? That's pretty awesome. And then for later measurements, with quote unquote satellites and stuff done at altitude, et cetera, where there's less refraction, they say that they can get down to they can break a degree down to 3,600,000th of a degree, and then 3,600,000,000th of a degree for the micro arcs. So shout out to the lads with those with those numbers. But anyway, the most familiar stuff we're going to be dealing with is arc seconds and arc minutes here in degrees. All right, so space-time tensors and geodesics and all that. So everything in general relativity is done in absolute differential calculus, and they use tensors for that, which I'll show you some examples of that. We'll get into what those look like. So they basically just have little matrices, coordinate systems, where they can look at like an infinitesimally flat part of it and then do all kinds of stuff. It's just matrices inside of little number or letters, right, that represent another matrix. All right, so to kind of break that down, what that means, to give some substance to it, would be, say you have an I-beam, right? And you want to describe a stress relationship between this part of the I-beam because it's going to be under X amount of load. It's going to be experiencing this amount of heat because it's near a pipe or something, right? And then over the length of that beam, you want to compare the stress points, right? So you can put a dot here, you could put a dot here in the I-beam, and you could use a matrix to describe those positions, and then you could mathematically introduce your stress and all that, and the resistance of the material, et cetera, would all be represented through this type of tensor calculus. Like, so it has practical applications. It's not like, complete abstraction, right? It has, like, this would be what it's used for, right? So and what they use it for in space time, right, is they put dots in their little coordinate system and they draw angles between them, essentially, right? So
let's start with that.
We got, I think that pretty much covers it. There were some videos, but I don't think we need to watch these now. They're pretty much summed up what they say. All right, so when we get into space-time general relativity metrics, there's the Schwarzschild metric, there's the Kerr metric, there's the FRW metric, and then there's different curvature metrics that you can use. So you could use flat space-time, you could use curved space-time, depending on the the magnitude of what you're trying to calculate, right? So if you're trying to calculate the relationship between distant galaxies, you would use a specific metric for that would allow you to account for the whole, the influence of the entire universe as a whole versus like just sections of it relative to like what you're calculating. So like just these two galaxies. So you would change the boundary conditions or the input conditions, which are these tensors or metrics, and that's how you would derive your solutions for the problems, right? So whatever the application is, you would use the appropriate metric. So starting off with the Schwarzschild metric, this describes space-time outside a spherically symmetric, non-charged, non-rotating mass. So what they do, for example, which we'll get into with the perihelion precession, what they would do to calculate the precession of Mercury going around the sun, right? They would calculate the sun as a stationary mass, non-rotating, no charge, nothing, right? Because all of these things would affect, due to the equivalence principle, would affect how you would calculate the gravitational field. So it's kind of like just kind of imposing the ideal conditions to calculate things, right? Essentially for the application of what you're trying to do. And if you're like, wait a minute, that doesn't sound that impressive because we know the sun's not that. This sounds super kinematic. Well, yeah, that's it. They taught everyone kinematics and they think it's dynamics and they're super impressed with themselves, and they can literally swap out anything to describe any phenomenon that they want to. So this is why the gravitational redshift prediction is like the most important part moving forward. And then we got the Kerr metric, and I'm just not going to touch on the others because they're not super important to what we're going to talk about. But the Kerr metric would be used for, so say you wanted to account for something that's rotating and has charge and all that, right? So you would hit up your boy Kerr metric, and you would use that to calculate the relationship. So they use this for two coalescing black holes. So if you guys have ever met the boys over at LIGO out there taking their measurements,
Shout out.
they would be Kerr metricing, right? Because otherwise those black holes aren't going to coalesce because the improper use of the coordinate system, right? All right, 1 second here. Gonna get some water.
Those LIGO boys.
All right,
love us.
Yep, and we got shout out to Matt Damon over there solving some linear algebra. Very cool. All right. Now we're going to get into the aspect of how do I measure the gravitational redshift, right? What is a redshift? How do you measure it? So what they have here is your standard issue Royal Astronomical Society telescope, right? And you point that bad boy to the sky and it hits a collimator. So you focus in that starlight real fine, and then you hit a diffraction prism, and it's going to go ahead and split that light beam for you into a rainbow. And then you're going to look for specific shades of red or blue within that rainbow. Right? So that's pretty much what they do. And that's it. That's it. So based on the frequency of light that they're looking at, they're like, oh, XYZ must have happened to cause this shift. So, for example, for the ether mechanics, right? you would say that relative motion through a field in interaction with that field causes the shift, right? So, for example, we'll get into later on, we're going to get into an electric field and a magnetic field and how those will cause frequency shift and wavelength shifts. So, we have an actual mechanism for the interaction, right? And they're saying here, right, they're going to put time dilation as their mechanism. So, that divergence from proper time in a graph that we saw is how they're going to explain it. How do I get back to the thing? Okay, yeah. Okay, so that's how they explain it. Right? So their mechanism, and keep in mind time dilation is a second order effect, so it requires a velocity mechanism or a gravitational field in their case. Like there has to be something to cause something for there to be time dilation, right? Time dilation isn't just the thing, right? So it's important to note that. So the velocity component would be a first order effect, and then a time dilation effect would be a second order, right? So what they're saying here is that as light's passing through a gravitational field, right, that's having the equivalence of a first order effect of velocity on it, essentially, such that it's appearing that it's changing the frequency or wavelength of light, and then obviously then they have their inverse proportional relationship to maintain the constancy. But within that, that's how they explain it. All right. Any questions so far?
No.
Cool. All right. So let me share this with sound, and we could watch the video on this. Give me 1 second. All right, so this is just a quick introduction to the Doppler effect, because this is going to be relevant to their frequency measurements and how they're applying their measurements with light.
The Doppler effect. In Sheldon's words,
Can you guys
the
hear
Doppler effect.
You guys hear the audio okay?
Yep.
Fantastic.
In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency.
All right, and this is really important because the medium here, air and water vapor, right, the medium which the sound wave is propagating through is what's facilitating that wave compression, right? So that's very important for how this works, right? There's a mechanism here interacting to facilitate this, right?
So that is the Doppler effect, the apparent change in the frequency of a wave
Oh, and shout out to Sheldon.
caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Yo, did you guys get something out of that? Let them know in the comments. All right. So let's see here. I think that was a pretty good explanation. And then we'll get into... Yo, what's up?
Sorry. I saw a picture this morning that was released according to the James Webb Telescope, or I think it was. Apparently, the whole universe is redshift. Nothing but black holes now. You seen that one?
Nah, that's awesome. Yeah, they're definitely going in some weird direction with it, especially with the James Webb. They're like putting out all kinds of, stories that are like, oh, we debunked our own cosmology and all this crazy stuff. So they're definitely setting up for something. It's all very interesting. All right.
Yeah,
so,
I saw one this morning.
Yeah,
like
we're in the middle of a presentation too. So. All right, so we have standard observational conditions here. This is going to be super important to the measurements that we were talking about earlier. So those arc seconds and arc minutes. Viewed at a high power from our ocean of air, a star is a living thing. It jumps, quivers, ripples tirelessly, or swells into a ball of steady fuzz. Rare is the night at most sites where any telescope, no matter how large its aperture or perfect its optics, can resolve details finer than 1 arc second. More typically, at ordinary locations, is the 2 to 3 arc second viewing or worse. And that's from Mac Roberts, Sky and Telescope Magazine, 1995, right? So to kind of give some context of what these lads are working with in the 1900s, and moving forward, right? It's all just an ocean of air, right? So shout out to the ocean of air. Equivalence principle, special relativity, and general relativity. So we kind of already went over how I don't know if I went over it already, but in general relativity, they treat acceleration as a gravitational field, right? And through the equivalence principle, they can mathematically link that to special relativity. So they're mathematically joined together, right? In that regard. So so anything that's a velocity effect, they can go, oh, you know what? That's also your boy a gravitational field, which gives us our time dilation divergence, right? So that's how they can start to explain velocity first order effects with second order time dilation effects, right? So this is how they get into that, because the special theory deals with relative motion and linear velocities. So when they're moving at uniform speeds. All right, any questions?
No, I don't think so.
All right, cool. So now we got our prereqs in. We'll get into the proofs that are put forward, and we'll analyze what they are. So the first one was the perihelion precession of Mercury. So to look at what that looks like. Imagine, I think I have a better slide for it. Yeah, right here. So imagine the sun, hanging out right here. Then we have the equatorial line, and then we have Mercury. And imagine every year it just passes over, and you can just see Mercury over the equatorial line by 1 pixel, 2 pixels, right? You're like, oh, no way, that's crazy. It's there, it's there always. But then over 100 years per se, you keep these observations going, and you notice that it starts to drift up a little bit. And you can start to see more than just 2 pixels, right? So that's what the perihelion precession is. This is what they say they observed in the sky. So as the story goes, a guy named Urbain Le Verrier in 1846 made 40 years of observations. 1 second, I have to blow my nose. It's driving me crazy, boys. I've been trying to ignore it, but I can't.
All good.
It's boogerlicious.
All right, man. All right. So as the story goes, your boy Irvine is looking at the sun for about 40 years. He notices that Mercury's seems to be doing that precession thing we were talking about earlier, where there's some divergence from its normal equatorial, uh, orbit. And when you do the math out, it comes out to be 5,600 arc seconds over the course of a century, right? So what that means is over the course of a century, Mercury precesses by, I think it's 1.25 degrees. So if we're calling back to the protractor, it'll be a full 1.25 degrees instead of these like arcs and minute arcs and all that, right? So an actual degree. But obviously this is super small because it has to take place over the course of 100 years. So the Newtonian prediction for the model of the solar system and how they use gravity, they could not. This is their story, right? Because obviously you can use math to explain anything, but this is like, this is the struggle. So they're like Newtonian gravity can't explain this perihelion precession no matter what we do, guys. If we add up the mass of all the other planets in the solar system and we play like a tug of war with the sun and Mercury, we can't solve this. We're off by 43 arc seconds. We can't do it. Right. And then Einstein steps in and he goes, ha, well, I can bend the old space-time curvature, dilate a little time, contract a little length. And what do you know? 5,600 arc seconds is my output. And everyone was like, oh, no way, dude. This is a real good proof of your theory. This means something. This is awesome. So everyone was super pumped about that, but they still had a hurdle to overcome because this is post-dictions, right? This isn't a prediction. If it was a prediction, it would still require some more substance. But this is everyone knew what this was, but this is like phase 1 to rolling this out, right? Because you gotta get everybody on board. All right. So this is the diagram that I made in Paint from that. Okay. So that was the story as we're told, right? But there's also another story involving a gentleman named Paul Gerber, who 17 years prior to Einstein giving his solution for the perihelion precession, Gerber put this forward using Newtonian mechanics. And what he did was set the propagation rate for a gravitational wave to the speed of light by multiplying them here together in this equation. So this this little t here is supposed to represent the propagation rate of the gravitational wave, and that speed delay from the wave, like putting a speed on it. It allowed for that 43 arc second prediction, right? Because it's gonna take a little bit of time to get there, right, or whatever. So like, oh no way, they did it, guys. We can keep Newtonian dynamics after all. Well, nah, nobody was interested in that because that was too akin to the Æther, which they were kind of walking away from, and the setting their propagation rate through light. They weren't feeling that, right? Is the story. Now Einstein comes along, and I don't know if you can I wish I could zoom in on this. Is it possible? Can it be done? Oh, hell yeah.
Oh, wow.
Nice. Shout out to whatever this is, PowerPoint. Okay, so now if we look here closely and get our detective hats on, we can see that these equations look very similar. Guys, one of these equations is just like the other. Remember, you guys heard that song from Hoobastank or whatever, whoever sings that? One of these equations is just like the other. I don't know. But anyway, so what Einstein did here is he capitalized this T, right? And he just replaced that with the periodicity of the event, right? And using that metric, right, where you can get that output, that proportional output, that's how he explained it, right? Along with that, when you put it in with that's it. That's all he had to do. It just outputs it from a proportional ratio from the event. Very, kinematic, you could say, right? We've seen this before with the GMM over R squared and all that. Same thing. Now, Einstein says that he didn't plagiarize this and that he derived this himself, even though he never showed it, right? And then they Paul, he gets called out for this. He goes, "No, I didn't derive, or I didn't plagiarize this. This is my own derivation. I couldn't have possibly done it or derived it from or stolen it from Paul because he's incorrect." Like, buddy, they're the same. Dog. What? Like, okay, dude. So we all can see that this is like the same thing. All right. So that's all he had to do to get that in. And then let's see, tap here to see the event. Okay, so we already went over basically the whole narrative, right? So in conclusion here, we see that it was totally possible to solve this. Like, this is all kinematics in the sky, but they needed to piggyback off of the backbone of special relativity with the equivalence principle to add on to the validity of it, so they can continue explaining things under this mechanism of length contraction and time dilation, even though it's all based off of an experiment where they didn't measure a velocity to even provide the time dilation, but they just interject the framework on top of that and go, look, this is the answer. So to make reality conform to that entire framework, they had to swoop up acceleration. So this is what this is. So nobody was interested in Newtonian solutions, right? They were looking for your answer is in a new coordinate system, son. Right? So that's what they were looking for, a new framework to get into. All right. So after the Paul Gerber debacle, right, there was like 5 other solutions that were submitted over a period of time, one of which is the Schwarzschild solution. So earlier I gave the example of, say you wanted to impose ideal conditions on an event to, explain arc second, to explain a 43 arc second or 5600 arc second perihelion precession or something like that, right? So you would hit up your boy Schwarzschild, fill all that in, and all that does is it basically just describes the sun as a stationary, non-rotating, no charge, nothing like that, specific ideal conditions. And then it calculates Mercury as if it doesn't weigh anything, like as if it's a photon just traveling along space-time curvature. And that's how they explain it. And it's all done through, and like earlier I mentioned, so they're putting dots on the coordinate system and drawing angles to them. So this is what all this is. And then they have the gravitational influence between them. So when they talk about the bending and warping of the fabric of the space-time, it's a really cool story, but it's the bending and warping of the fabric of the coordinate system, or of the graph you're using to represent the divergence in time due to the gravitational field or the acceleration you may or may not be experiencing in your reference frame. All right. So I think that sufficiently covers the perihelion precession. So what we learned here is that this is a calculative answer. It's purely a postdiction, right? It doesn't mean anything. They actually stole one guy's equation and just completely reused it. And then they came up with a way to use specific metrics where they could impose ideal conditions to give the output needed, right? So very cool. Very cool. So now we're going to get into the deflection of light rays with gravitational lensing. So this is, everyone gets real excited for this one because these stories are why when you Google gravitational lensing, you see the James Webb Telescope images, you see all the abstract art of all this crazy amounts of bending light that guys, the amount of bendy light. You guys want to talk about bendy light for a second, dude? Go to Google and type gravitational lensing and look at those images, right? That amount of bendy light is insane, and no one's ever seen that with their oculars, bro. No one's ever put their eyes through a telescope and seen that. When the measurements that we're going to get into over this narrative and what they've convinced people is possible over an event that may or may not even happen is kind of cool, man. It's kind of cool. All right. So the idea here is that on Earth, you'll be looking at a star, and then there'll be some sort of gravitational influence. In this case, it'll be the intersection of the sun's gravitational field, and it's going to change that actual position that you would see it normally to an apparent position, as if like, so you know how they say in a Sagittarian eclipse there's an amount of refraction that lifts it up like 5 degrees or something like that. So very similar concept, except not to 5 degrees. It would be much smaller. But that's kind of what we're looking at here. So they're saying that as a gravitational influence or whatever gravitational field goes by that starlight, it would change its trajectory, right? Similarly to how they calculated the perihelion precession, right? So you would have the mass of this, the image is kind of blocked out or darkened from the thing, but like let's say we got this galaxy here and its mass is bending space-time, right? So the light that's coming out of it is going to travel along the curvature of that light, because in relativity everything is traveling along a geodesic. So it's really, it looks like it's, what is it? What do they say? From your perspective, you think you're traveling in a straight line, but you're really traveling along curvature. So one of the examples they would give would be, say you're an ant on a basketball. From your little tiny ant perspective, you're like, oh, straight line forever, bro. But from our perspective, where we can see the three-dimensional sphere of the ball and all that, and the ant traveling along, we can see that the ant's on a curved trajectory, right? So that's kind of what that's exactly what they're saying here.
So how would the ant then make an assertion about the curvature of said line?
So here's what the ant would have to do, right? The ant would have to go take a measurement with an Æther pherometer, right? And then he would have to get a null result for his measurement. And then he would have to convince everyone he got the null, because he's experiencing two mechanisms that happen due to velocity when it's measured. But in this particular case, the reason why the velocity wasn't measured is the mechanism for the measurement. Yeah.
So as long as
yeah.
As
long as the ant's super crafty, like you can explain anything.
Okay, so he couldn't actually substantiate it, but he could go make a bunch of claims about it.
And he could even come up with a mathematical coordinate system that establishes covariance with an already established kinematic system. And you could use that to bolster the ant's claim that he's making dynamic descriptions of actual emergent, or pseudo forces that are emergent properties of space-time curvature. I used a bunch of air quotes. You can't see it, but the stream can see it, so we're good. But yeah, that's exactly what the ant could do if he had enough paper to write on with his little ant hands or whatever. Because that's a lot of math for an ant to do, but it could be done.
Okay, any ants out there listening, there you go.
All right, cool.
Relativistic ant.
All right, so we're going to introduce the characters here. This is Arthur Eddington, who set out on an expedition to look for gravitational lensing. So the story here is that there's a prediction made by Newton by how much light would deflect due to the interactivity on the level of like a mass attracting mass, so to speak. Excuse me 1 second. With a mass attracting mass kind of mechanic, because Newton was a proponent of light being a tiny corpuscle. So he was thinking that light would be acted on by, like a mass attracting mass situation. So the prediction for Newtonian mechanics was that light would be deflected during a solar eclipse by 8.7 arc seconds, right? So really tiny amount. And then the Einstein prediction was double that at 1.75 arc seconds. And the mechanism would be that the gravitational field would, cause space-time and curvature, and the light would have to travel in a curved path to hit your eye. And that displacement would change the apparent location by 1.75 arc seconds. So you're saying if they're looking through a little telescope, it would be deflected by twice the amount the Newtonian prediction. Okay. All right, so this is the man that went out and made the observations. Him and his boy Cromlin. I don't have a picture for Cromlin, but we'll get into him in a second. Okay, so the expedition was a complete wash. So what is it? Eddington went to the west coast of Africa, and his boy Cromlin went to Brazil. Cromlin took 16 photographic plates and 16 like before and after plates, so he took 36 altogether. No, I'm sorry, 16, and then he had before and afters, so 2 sets. So anyway, all of those they say can't be used because during the eclipse there was a temperature differential and his apparatus physically contracted, right? Like due to due to the temperature change. So the measurements they like, oh, we can't use them at all, boys. Like none of them, not a single one. So we can only rely on our boy Eddington here. Like, so that's cool. So Eddington, so we can already see where this is going. So Eddington's got 16 plates and 16 reference plates, so 36 total. And wouldn't you know it, none of those are good except for 2 plates and none of the reference plates. So the before and afters, right, were taken with the same type of material so that you could get like a better transfer when you're trying to, compare the measurements and whatnot. So all of those didn't work out. And he just had these 2 plates. So he says he gives on his way back home, he writes a couple letters to the boys back at the Royal Society, and he's like, lads, all the pictures were pretty crap except for these 2, and even these don't look good, but we'll get back to, we'll have to figure it out when we get back. It's not looking good though, right? So he gets back to the Royal Society. Him and the boys, Frank Dyson Watson, get together, do a little mathematic transformation, little finessing, little massaging, and wouldn't you know it, they find relativity theory. They find confirmation of it. And they find that they announce that this is a glaring success for relativity theory, these 2 photographic plates. Now, sadly, the reference plates of the same material used for the actual picture plates didn't make it. So they had to use photographic plates used from a different material taken from like a year prior. So they came up with a way to, compare everything and contrast it. And anyway, long story short, relativity is super true. So here we are 6 months later from the observation in June.
So the same photographic plates that they say were the ones that proved the relativity theory, they didn't use those they didn't analyze those, they analyzed ones from a year prior.
So for the comparisons for where the stars would be, they used the ones from the year prior. But for the proof, so called, they used the 2 that he took on site.
Well, that's weird.
Yeah. I mean, sometimes you have scientific anomalies. Sometimes there's a temperature differential and all of your photographic plates are just a complete wash. Like, these things happen in the field. You can't really, draw too many, make many more excuses than that. So before it becomes super unreasonable, right?
So
we just got these
2. General relativity confirmed.
Yeah. So we're here at November 6, 1919. The boys from the Royal Society and the Royal Astronomical Society are getting together to give a confirmation of the general theory of relativity, and thereby mathematically merging it permanently to the special theory and confirming in perpetuity the heliocentric model forever. And the correctness of, and by extension, right, the dynamics of, Newtonian gravity, which we already know failed interferometrically in 1887 and many more, right? Like through the history of all of them. So it's all just kinematics, but this is the expansion. This is the kinematic expansion pack to Newtonian to Newtonian dynamics, right? So I'm using air quotes for dynamics. Okay. So here we go. So we'll introduce some of the characters and give, just kind of read a little bit what they say. So this is from a transcript of these lads. So I kind of put pictures to them. Some of them aren't important, but I included the full back and forth for the relevant argumentation, but some of the stuff's less important, so we'll skip through some of it. So this is Sir Joseph Thomson, president of the Royal Society, and he says, he comes out, giving a successful confirmation. This is the president, right? He's like, boys, we did it. He gave him the old LIGO speech. He's like, boys, we did it. We confirmed relativity. Woo, woo. And everyone was super pumped. So he comes out.
Have detected gravitational
Lens.
lensing.
Yeah, dude, exactly. So he gives his successful confirmation, right? And some other lads chime in here. See, we know that the momentum carrying in different blah blah rather than the Einstein. So here he's bolstering his measurements, and then he's trying to downplay any possibility of refraction or anything like that. And then we get into, let's see, Frank Dyson Watson. Oh yeah, so this is the lad who helped out with the photographic plates, did the old mathematical switcheroo, and we're gonna get into how bad he cooked the books here in a minute, because it's you know, it's a classic Frank Dyson Watson, really. So he's so let's see here. We're going to do Alfred Fuller from the Astronomical Society. I've looked 100 times quality of the probable error. Okay, yeah, so this is important. So now what we don't know about the gravitational lensing experiment is that in tandem with that, two gentlemen, John Evershade and Charles St. John, were doing spectroheliograph observations looking for the gravitational redshift. So earlier we were talking about take your Royal Astronomical Society telescope with a collimator and a prism, and you split a rainbow out of the light beam, and you look for the a specific shade of red or a specific shade of blue and whatnot. So these lads were doing that the whole time, and prior to this too, right? Because they had the equipment and they had different phenomenon in the sky that they could use to make these redshift observations and predictions. And let's see, they don't include like any of this in the history, really. They don't talk about this, but these guys were completely they basically wouldn't cook the books and confirm relativity theory, and every time they would take their observations, they were not in alignment with relativistic predictions. So in order to establish a cause and effect relationship between any gravitational lensing displacement, you would have to have a proportional amount of gravitational redshift due to that relativistic mechanism, right? And that's all predicted in their math, which I kind of skimmed over real quick. But in these metrics, in these solutions, one of these outputs gives you the frequency that light should be due to the influence of the gravitational field, right? So this is the factor that it's, right here, 2gm no 2gm over RC squared. I don't even think that's it, so we'll have to come back to that. Ignore that part, but they do get their predictions out of the space-time metrics, right? So these are supposed to be proportional to the to that amount of displacement, right? So it all has to be in alignment. You can't have one without the other, right? Because one causes the other, right? So otherwise you just have, more kinematics, right? So this was a very important part of this. All right. So where was I? Okay, right here. So this guy chimes in during this meeting. So a couple guys gave some objections, and we're going to go over what they brought up, right? Because they already gave, the president went out ahead and already gave the successful confirmation. So they're rolling it out, but they wanted to, a couple guys raise some points here. So we're going to go over the interesting stuff from the gravitational redshift, readings that were completely absent from the proof that would be required to substantiate space-time curvature as the causal mechanism for the displacement of the starlight that they claim to have observed. Okay. So Professor Hallard, president of the Royal Astronomical Society, says, the quantity looked for, I may say, is 100 times the probable error of the measurement, which may be made with the large spectrographs now employed with such inquiries. Evershade has also examined the light from the sun, from the far side, or from sun away from the Earth by photographing the spectrum of Venus and on the further side of the sun. So basically, when it's doing its transits in different positions, he's taking observations, looking for that redshift. Like, when are you coming towards me? When are you coming against me, right? Or moving away or whatever. Anyway, so gravitational displacements, if they exist, should appear in all parts alike, but he finds no such displacement. on the other side of the sun, though he does get a slight displacement on the near side. It is very desirable that these spectroscopic tests be carefully repeated. So again, that the substantiation of the physical mechanism to even justify any of this, right? Then Lindman chimes in. What does this guy say? He says something about nothing super important. All right, this guy talks about this guy proposes that so earlier when Eddington's like patting himself on the back, he also goes, yeah, there's also no other mechanism that could possibly cause that displacement near the sun. And this guy's like, well, that's not true. You could get into what would it be? The electromagnetic field. So the electric field, the magnetic field, the corona, plasma, because they thought there was plasma there. So they already had a medium in the spot where these measurements take place. Because guys, we haven't even got to where these measurements, like the distance that they were at away from the sun were, right, for the predictions. Because like we're all probably thinking like gravitational lensing on the sun, like that. Guys, it's crazy. It happened within the solar limb, these measurements. So not like oh, we were looking out in the sky and we saw a star move. No. Literally on the solar limb. So they're having a back and forth here, like, hey, maybe that was from the corona, maybe it was from the electric field, magnetic field. There's a lot of density. We don't even know the conditions. How are you gonna sit there and assert that, sir? Right? Because that's how they talked back then. It was like, sir, or whatever. And this guy chimes in again, and he's useless. This guy might as well not even have been there. And I'm just kidding. It probably said something cool, but it's not relevant for this. So this guy chimes in with the biggest debunk, right? Or the biggest evidence put forward. So this is Dr. Silberstein, who I dub Whitsitt's great-grandfather for literally no reason. I just kind of think that there's some resemblance there. I'll let you be the judge, though. So we'll just read off his quote here. So he says, but in spite of what the president said, I believe this result to be essentially an isolated fact. There is a deflection of the light rays, but it does not prove Einstein's theory. It cannot logically be deduced from his theory as a gravitational effect in absence of the spectroscopic results. So in absence of those gravitational redshift readings to support this, right? So he says, and as so far as we know from St. John in Evershade's observations, the predicted shift of the spectrum lines of an amount exceeding almost 100 times the amount of probable error of the modern spectroscope, just as Professor Fowler pointed out. So shout out to Fowler. He also pointed out that they had the capable means to make the measurements, is not obtained. Professor Lindman's attempt to explain the obstinate nullity of the effect by the motion of the luminous gases in the lines of vision is not satisfactory, for St. John's was well aware of the complicating circumstances. And real quick, these guys, Evershades and St. John were like the masters of the Fraunhofer lines is what I've read. So like looking at solar spectrum readings, looking at splitting light into a rainbow and looking at it at this time, these guys were the guys. These were the rock stars in spectroscopy. Right. So their opinions, what they were weighing in on mattered a ton. So let's see here. So they knew exactly what they were doing here. So he says we were aware of this, and therefore we purposely observed as many as 43 lines at the sun and almost as many as 35 at the limb. So they took multiple readings so that they could, figure it out. No, we cannot well assume that the gas moves everywhere toward or away from us only to suit Einstein's theory, i.e. to compensate for his theoretical shift. As I have pointed out on another occasion, if there is no spectral shift in the coefficient for the spacetime curvature, which is entirely responsible for it, then it must be unity. So it must go to zero. And that means if there's no curvature in spacetime, if it goes to zero, then you can't travel on a geodesic, right? You can only travel in an actual straight line, which is a problem. So let's see. We must. Okay. So it must be unity. And if we go back to the differential equations, Einstein's field equations, we shall see at once that the other coefficients in his well-known approximate solutions become unity of the same. So he's given the bendiness of space-time in relation to the divergence of the world line due to motion or the gravitational field, and like the equations are written out. I just summarize what they did. And since the equations of motion are always given by these hypothetical number, or like I forget what it's called, but it's when you just use imaginary numbers. When these are given to zero, we see ultimately that the spectrum shift is absent in Einstein's theory, and it does not give such refinements for the planetary motion as in the secular motion of the perihelion precession, not even the ordinary Newtonian or Keplerian motion. In short, the planets would be straight lines, and the planets would move among them. Let's see. In short, the orbits of the planets would be straight lines, and the planets would move along them uniformly despite the sun's presence. The theory stands or falls on the correctness of the results of Evershade and St. John. All right. And then he goes on to say it's unscientific to assert this, in its present form. We should think clearly before modifying Newton's laws of gravity. This is, and he's just saying that he's again reiterating that they have the technology to make the measurements within the means of probable error. And let's see. Yeah, and if the solar shift is unproven, if the spectral shift is unproven, then the whole theory collapses, and the phenomenon we observed by the astronomers remains a fact awaiting to be accounted for in a different way. So the importance of this, like I was saying earlier, they needed this to substantiate the displacement in the first place, right? Because we're all told the fantastical story, but how many of us are told about the history of gravitational redshift? Right? All right. So let's see. Doppler reading. So we already went over that ad nauseum. So Eddington gives a little rebuttal here, and he says, "Look, man, quit being a buzzkill." All right, I'll read the actual quote. He says, "One word, Dr. Silverstein. When a result has been forecasted and is obtained, we naturally ask what part of the theory exactly does it confirm? In this case, it's Einstein's law of gravitation. It is not necessarily that his theory that is confirmed, but with the underlying assumption that the space-time coordinate system interval is a quantity to be measured, right? Like the curvature is a quantity. The assumption that the curvature of space-time is a quantity measurable by clock and scale. There still remains the question of the intermediary of what the quantity of space-time is, which must be tested by the Fraunhofer lines." So he's saying, look, man, we saw the displacement, but we don't know how it interacts with light. We need to do more Fraunhofer line testing, and that's just the old way they used to say more spectrograph readings. They need to split more rainbows. Right.
Yeah, so I mean, not only is it explainable via classical causal mechanisms, but it's not even like well measured in this particular case.
Nope. And
And
we're about to
so-
get to the
Yeah,
we're about to get to the punchline too on the measurements.
it's funny how they the quote DS. That's quite
Yeah.
fitting.
Yo, straight up. Absolutely.
Dog.
Yep. Okay, so real quick, Eddington, 6 months prior, before he went to do his observations for the eclipse, he wrote to a Swiss mathematician, Hermann Well, and he said, "Hey, man, the boys St. John and Evershade have been going hard on these Fraunhofer lines, and they're ending up with full DS and not the kind we're looking for." So I heard you have a new unified theory that you're working on, and you could possibly explain the lack of the old Fraunhofers. Let me know what you can do, my dude. That's me paraphrasing what he said there. So even Eddington had his own reserves about the old Fraunhofer lines, right? And again, the Fraunhofer lines. Yeah, we're gonna time travel back to the first slide. So when these readings here, we'll get right. So when there's displacement within these lines and they do spectroscopy and they're like, oh look, there's helium gas, there's neon or whatever, right? This is those are called Fraunhofer lines. So when they're talking about the spectroscopy readings and the spectral readings and making the rainbows, they call it Fraunhofer lines. All right. Yeah, back to Eddington. All right. All right, cool. So the very next day, November 7th, 1919. So this is after they already announced the successful confirmation. We have two photographic plates that may or may not have been mathematically manipulated to give the desired result. We have a lack of a substantive mechanism to cause the displacement or to cause the frequency shift or wavelength change in light. And we have an alleged displacement. And that's all we got so far. All right, so November 7th, 1919, the Royal Society and Royal Astronomical Society announced to the media, so the British media and the US media, overnight announced that Einstein was, the smartest person in the world. His theory had been confirmed. He beat the game. The laws of the universe obey space-time curvature. He was the new man. Right. So we have here H. von Kubler from 1960, Vistas in Astronomy. It should be noted that the deflection predicted by Einstein in 1916 was very small, being about 1.7 seconds of arc for a ray of light at the edge of the sun, and inversely proportional to the radial distance from the center of the sun. Since no star for which the measurements were made during the 1919 eclipse were made within 2 solar radii of the center, the largest deflection that would have occurred, according to Einstein's theory, would have been less than an eighth of an arc second, right? 0.8 arc seconds, for which the 343 centimeter focal length of the telescope used by Eddington would have corresponded to about 0.01 millimeters or 0.00039370008 inches on the photographic plate. So we got a real problem here, lads. At the solar limb, the largest amount of deflection that could have occurred couldn't possibly have been 1.7 arc seconds, and that's what was needed to make a successful distinction between Newtonian gravity and its interaction with light and space-time curvature. So let me see if I can. So say there's a star out here, right? It would get displaced by 1.7 arc seconds. But say under general relativity, but say there's a star here, right? It couldn't get displaced by that amount. And that amount's the only amount that would be confirmation of his theory. And the measurements actually took place at this spot here, right at the old solar limb.
Right where you have a massive medium fluctuation.
Exactly. So this is what they're working with right now. We've all I'm sure that before this point in time, we've all abstractly, intuitively thought of like a gravitational field bending and warping space-time around it, and stars moving in different directions. As this ball goes by. Not at all. It's literally only happens at the literal rim of this, right? And like Toby was saying, where there's already speculative, where they already speculated there could be a multitude of other things to cause that. And one of them, right, we just learned mathematically couldn't be gravitational displacement or space-time curvature, right? So, all right. So that's huge, right? And keep in mind, like, remember how we had these photographic plates that couldn't be used, and it came down to these two plates. And thank God we had these other these backup plates and Frank Dyson Watson could come up with the coefficients to do the transforms, to do the error corrections for everything, and do a statistical analysis on it, and make sure that they didn't fudge the numbers, and make sure that the analysis of the difference between the two materials and the plates and the transformations of the measurements was all lined up. And god dang it if they didn't just get enough arc seconds to to confirm relativity, right? And it literally couldn't even have happened in that area to that magnitude. All right. And then we have just some more people chiming in on this. So Dennis Sima says, this is a famous lad in the physics community. He says 1967, he says, the first attempt to test Einstein's prediction was made by a British astronomer led by Eddington at the end of the Great War, at the time when it was very striking that a British astronomer should be attempting to test a theory by a Yeoman, and the results were tested and claimed as a triumph for Einstein, and his worldwide fame dates from this event. Ironically enough, attempts made at later eclipses suggest that Eddington underestimated the difficulties and uncertainties inherent in such observation. And even today, Einstein's predictions have not been tested with the precision one would wish. So they've made subsequent observations of this throughout the years when they can, and it's only within the solar limb, right? And we have John Maddox chiming in on that says, like, he would like to see some more successful measurements of it. And then we have Edward Dowdy here, peace be upon him, passed away recently, a couple years ago. But he published some papers here, and what he was saying, this is the reason that he became a plasma cosmologist, because when he looked into gravitational lensing, he realized that it only happens within the solar limb. It was outside of the confines of the prediction of general relativity itself. And, he was like, well, the sun's plasma, right? So, everything started clicking for him. So this is why he changed, right? This is why people change cosmology. When they actually look into the stories behind it, they actually understand like what happened, what they're claiming. It's not a tenable position to hold. And, shout out to him for becoming a plasma cosmologist, right? And there's a link here to a cool video from him where he gives an interview on this. If you guys want to check it out, it's on Sky Scholar. It's about 8 minutes. He's a little stiff in the interview, but that was like his first time on camera doing that or whatever. But he was a cool dude. All right. So again, kind of like I was saying earlier, we've all thought about the displacement. We've all conceptualized it happening at far away distances from the sun, but now we know that it happens within the solar limb. All right, some more people saying that it's a real shame that Einstein's theories are confirmed and put forward by this, and it's a real travesty. All right, so we got a displacement that may or may not have happened, and we have no mechanism to change the wavelengths to correspond to facilitate gravitational lensing, right? So the gravitational lensing proof actually comes after. But we'll get to that a little later on here. Oh, look, we're there. Gravitational redshift. We're there. Okay, so in the video we watched earlier, they kind of already touched on it with starlight and how there's a frequency shift in it, and they're using that to take their measurements and tell all their stories about what may or may not have caused that shift. And we got some Fraunhofer lines, right? I hope we all adopt the lingo of Fraunhofer lines. I think we should all say it. All right, so let's see. Different types of wavelength shifts, or they attribute these to different mechanisms, right? And the distinction that they make, right, is they're like, okay, we're measuring it to a more precise approximation, right? So it's like we go from this red gradient to more red, right? And if you could analyze that somehow digitally, right, I'm sure there's like some sort of what would you call it, like a hexadecimal to represent the characters of the different spectrums, right? So like, so as your eyes stop kind of perceiving the difference, you could still digitally extract it or whatever. So that's kind of what they do, right? They just make these measurements. They look for a frequency of light, and then they tell stories about what may or may not have caused it. All right. So we're going to jump to 1960 now because it's been a long, cold time for relativity theory and gravitational redshift, and we need us a mechanism to make this theory viable. So we're going to go over Pound Rebka and Pound Snyder. Oh, sorry. Before we get into that, are there any questions so far? We've been over a lot and been kind of talking a lot. Is there any questions?
Real quick, if anyone's listening, and I had a couple people in chat saying that I was roboting my audio. Is it any better? Is it still roboting? I don't really have any questions though, other than that.
Cool. All right, we shall continue. So, at the old Harvard laboratory, the lads Pound and Rebka got together and they came up with an idea to do an experiment at the Jefferson Tower. What they had here was a quote unquote photon emitter, right? And then at the bottom, they had a photon detector. They would emit their photon from the top, and they had a predicted amount that should be that the frequency of light should shift by due to the difference in gravitational potential if general relativity is true and the gravitational field works as they mathematically predict, right? And keep in mind, there's an entire history of gravitational redshift predictions that that went back and forth where they it was like, basically, until what year was this? 1960, right? So until the 60s, it took to get the predictions down to where they could have something that they could all agree on and conceptualize as real. So anyway, these two guys, they got their predictions. They got their the idea here is that the photon coming down this tower its frequency should change such that due to the interaction of the gravitational potential, right? That it'll get emitted to this detector. Now, this detector they have only only detects a certain frequency, the way that you set it up. So if the photon is any other frequency, there won't be any detection, right? And the photon is just like the frequency of light. It's fine. So let's see here. So they have a predicted frequency of light that's going to come out, that's going to hit this emitter. And if it's not that, it gets rejected essentially, right? And then they also do it on the inverse. So they take the detector to the bottom, and then they take the detector to the top, and they take the emitter to the bottom, and they do the inverse readings. So that's the concept of the experiment here. And there's different quote unquote relativistic answers that are given here, but we'll get to the heart of it. So that's the first experiment that they did. Oh, keep in mind here. So this is really important, actually. You would think, okay, so how are we going to isolate this? How are we going to do it? Well, they actually needed to they had like a tube going down here to the bottom, right? They filled it with helium, right? So that they had a medium to interact with, right? Now. Yeah, dude. So so that was the first one that they did, and then they did another one in 1965. It was Pound again, and this time with another guy named Snyder. And with the first experiment, they couldn't tell if relativity was true or if classic mechanics was true, in the sense that the photon appeared to gain speed traveling downwards, and it appeared to lose speed traveling upwards, and in an approximation that would be in accordance with 9.8 meters per second squared, right? Like so. They're like, we don't know, because light's not supposed to change speed, right? It's not supposed to be faster or slower, because at this point they've moved on to relativity theory, but there could still be a frequency shift, right? So they were the first experiment that they did using the light spectrum. They were like, okay, well, we're gonna need to control for some variables, maybe Earth's magnetic field, blah blah blah, right? So they do this other experiment with gamma radiation, right? So what does that mean? Well, gamma radiation would be neutral to magnetic, like a magnetic field or an electric field. It wouldn't cause any, what would it, frequency shifts in it, right? So they have like a resonance cavity. They got some radiation or radioactive material. It's emitting gamma radiation down this tower, and now they've got their new readings with a more controls, right? So we're going to read here from their paper. So this is from. So they say here, it is not our purpose here to enter the many-sided discussion of the relationship between the effect under study and general relativity or energy conservation. It is not it is not to be noted. It is to be noted that it is to be noted that no strictly relativistic concepts are involved in the description of the effect as an apparent weight of a photon is suggestive. So their first paper was titled The Apparent Weight of a Photon, because like I said, they couldn't tell the difference in the frequency shift if general relativity was true or if light changed speed, right? Like in the classical sense. So people were complaining to them apparently. So they're like, look, man, we're not saying anything about the conservation laws. We're not saying about general relativity. We're just reporting on what we're measuring. So he says the velocity difference predicted is identical to that of a material object that it would experience in free fall for that time of flight. So the time of flight being the top of the tower to the bottom. And in this experiment, they were at a 75-foot tower instead of a 70-foot tower. I think the first one was 70 feet. This one was 75. So they go on to say here, that the view of the local timescale depends on the gravitational potential appears to require a coherent source for confirmation. The present experiment is unable to distinguish between the frequency change and velocity changes. For example, it appears that, it would appear as if an experimental comparison of clocks at different potentials would make a useful complementary contribution to this experiment. So, Toby, do you remember how Wang was like hooking atomic clocks up to an interferometer? And he was like, "Look, guys, it's going faster one way."
Yeah.
So this is the same problem. They were like, "Hey, we should have an atomic clock at the top and one at the bottom because the predictions are identical, and we truly can't tell based on our detector if C is moving faster than that's causing the frequency change, as if it's falling faster to, if there's some sort of preferred bias to the ground for electromagnetic propagation. Is that happening, or is the gravitational field real and it's having an energy exchange with it?"
Could be relativity, could be classical. Who knows? Who cares?
Yeah. So they gave these guys prizes. I forget which ones, but they gave these guys prizes for this.
Prizes.
Yeah, they got trinkets.
Of course they did.
Yeah, they got trinked out. So there's some like relativistic explanations given, but I mean, do we really need them? Because it's pretty clear right here in their own words. They can't do it, like they don't know, right? So people will say, need to go over these. Let's see. The interpretations put forward. So they'll invoke time dilation. They'll invoke the equivalence principle with inertial mass and gravitational mass. And let's see, gravitational redshift. So they'll invoke the curvature of space-time. Like you'll get all different stories depending on the relativist you're talking to and their awareness of the issues at hand. Seems to be the way relativity works when. So there's a couple different solutions here. So one solution is all photons move at c while exchanging energy and momentum with space. The photons shift their wavelengths gradually and move through the stationary gravitational field. So there's a drawing here of that provided, where the photons change their wavelength as they're emitted. They travel through the suggested gravitational field at a constant speed of c, and they are impacted by it, causing the descending photon to gain mass and momentum, and the ascending photon will transfer mass to the thing as the wavelengths will gradually move through the field. So they're basically just kind of explaining like the mechanism of what they claim to be
C
measuring.
is staying the same, but the wavelengths are just growing.
Yes, that's exactly, dude, Toby. They literally, it's an inverse proportional relationship where if one's going one way, the other contracts. So it never loses its speed. It just changes frequency as a function of its momentum conservation. It's like
Wow.
sick, dude.
Cool trick.
Light, bro. So another explanation here is all photons move at a different velocity and none move at c, which require the photon shift of the mover observer. So let's see. This contradicts the. I was about to say that doesn't even sound like it would be viable. So the explanation that's provided actually contradicts the constancy of the speed of light. So they wouldn't even be able to use that. And so the other one given is photons acquire the phase shift at source and move at c relative to an observer. So it's moving at c the whole time right up until it hits the detector, and then it's just magically a different frequency. All right.
Fun how that works.
Yep. So this guy he does some math for giving like the benefit of the doubt on like what the maximum amount of time dilation would be for something that weighed 1 pound at that gravitational potential at that height. Right. He goes through, does the numbers. It's actually in the notes portion of this. 1 second. So within the confines of the experiment, the gravitational prediction or for time dilation, like the maximum amount that could have occurred. I'm sorry, the measurement, the maximum amount of time dilation that this device could have measured that could have occurred that would have made anything perceptible to the device that took the readings would be 10 to the negative 15, right? And if you do the generous math, giving them, 1 pound and the gravitational potential at that altitude, you would get an effect that's 10 to the minus 21. So time dilation wouldn't even be perceivable.
Wow.
Like it's not even on the table. Right. And then one of the things that I thought about when I was looking into this, but I didn't realize that the purpose of the gamma radiation was so that it wouldn't interact with any electric or magnetic fields. But in the first experiment, they said maybe there was like an electrical or magnetic anomaly, et cetera. So to kind of touch on that, this is the Stark and Zeeman effects, respectively. The Stark effect.
You're not sharing with Discord.
Oh, right, because I closed the thing. Sorry about that.
All good.
I put it on note mode so I could read the numbers for the thing. All right. So we should be back. Oh, no. 1 second. All right, cool. So the Stark effect, an electric field will cause wavelength changes or frequency changes in light, right? So it can retard the light frequency such that it produces what they would call these Fraunhofer lines, what they would call red shift or blue shift, right? And the Zeeman effect does the same thing, but that's with the magnetic field. So the way they explain it through their convoluted reasoning is about, photon shells interacting as they're rotating past each other, but we can skip all that and just acknowledge it as a frequency shift within the wavelength or a wavelength change within the frequency. So the oscillation rate, right? So the oscillation rate changes, this color changes, right? Okay. So we have here a video from Ken Wheeler who shows electromagnetic retardation, right? So this is what the Stark and Zeeman effect essentially. So you have a magnetic field, or an electric field, you have electromagnetic propagation going through it. It's going to be retarded as it's going with or against the direction of flow within that field, right? So we have an example of that with a magnet and relative motion. I'm going to play a video from Ken Wheeler at a very specific timestamp. Let's see here.
I've made so many.
Share so we can all listen to the audio. We're going to go to 618.
The egg, which exists at a ratio.
All right, 1 second, Ken. Settle down now. All right, so 618 to 813. So even if you don't like Ken Wheeler, all right, if you're against him for some reason, right? You can watch this portion on mute and just look at the relative motion and the frequency change, or the color change. All right, so here we go. Take it away, Ken.
But how can I shift that relative motion to the disparity of the electricity, i.e. light, which is a coaxial circuit, transverse electrical magnetic, longitudinal dielectric? Let's show you phase shift. Now look closely and I'll explain it. You see how this is blue now? As it was approaching, it went to blue shift. If I move it away, let's just look at this one pole only. Let's ignore this pole over here, okay? You notice that this red shifted now? Let me move this closer to a person over here. Let's say there's a person on a little planet over here, and this is a star. Okay, now it's red shifted. Let's move the star closer to this person over here. You see how this blue shifted? Let's move it away and watch this blue, which is bluish green, but it's still blue shifted, turn to red. Red shift. Blue shift. We're only looking at this pole over here. A second. I think I had a little power outage there. There we go. Blue shift. Red shift. Red shift, moving away from this relative point. Now let's take a look.
All right, so real quick, my explanation for what's happening in here, right, is this LED ring is, it's oscillating, right? It's causing the, a frequency to illuminate here, and that frequency is being retarded by this magnetic field. And then as he's moving the, the lights over the magnet, that relative motion is causing a frequency shift proportional to, or, in regards to the going with the field or against it, right? So it's either retarding the light or giving it a boost. And that's what's causing the color change.
Let me check my power connection here. Let's take a look at the other pole. Hold on a second. There we go. Sorry about that. Let's take a look at the other pole over here on the right side. Let's orientate my magnet exactly. Okay, let's wait for it.
Oh man, I accidentally closed it. It's almost done though anyway. But here's a link to the video. Oh, nope, that's a link to a screenshot of what the link would look like if it copy pasted correctly. I'll get the link later. Let's see here. See, Silverstein was the most vocal. Could the relativity equivalence principle? All right, not sure what this part is from, so sorry about that. Michelson-Morley dynamics of G. So this was some stuff added later. We'll get back to that. Okay, electromagnetic retardation. So that's what we kind of went over earlier with the red shift and the blue shift and the relative motion and the frequency that's causing the illumination inside being retarded. Does he not have a RGBD LED in that? Yeah, probably. I would assume so. Feel better about it. Yeah, I'm not sure, to be honest. I think he does mention the LED strip that he has in the video, but yeah, that's a good point. So Ion said if it's not white light only or whatever, then he feels less comfortable about it.
I guess that makes sense.
But yeah, I mean, either way, the effects are.
You would still have red and blue shift, but yeah, it would be less straightforward, I guess.
Yeah, and thankfully, this was already canonized by Stark and Zeeman in the early 1990s. All right, so some stuff from Shane. Weighing the magnetic field, toroidal field, translational motion. Let's see. Okay, so this was like early into like Æther explanations to for mechanisms and for some of the stuff that they're measuring and like following toroidal flow and the magnetic field and all that. So basically, the proposition was if there's Æther that's flowing, that's going in the in accordance with the magnetic fields. So I had some videos from Shane, but honestly, we're almost done. So I kind of just want to wrap it up. But anyway, that was like the early conceptualization of the Æther flow following the toroidal geometry and whatnot. But anyway, and how it would translate the motion of the sky to the Earth and all that. like for these measurements. So anyway, that was some possible explanations for Pound-Snyder was just the ether wind, right? It's just a mechanism of the ether, right? There's a preferred bias from the like ether density, right? There's pressure, so there's a preferred direction going down, and there's also a preferred direction going east to west. Questions, comments? Although I guess I should say alleged frequency shift, right? Nobody put an atomic clock on it. So I guess you could still, I guess if you still wanted to argue that C is C, right? But my interpretation of that experiment would be there's a preferred downward bias, and there's also the east-west bias for the rotation of the sky.
No, I think you hit it all pretty well. And we even have, as you laid out there, we have classical explanations. So it's actually funny how things just make sense when you look at them through a classical framework.
Yep. And then, so we're going to get into some proofs of time dilation, right? So remember that time dilation and length contraction are second order effects. There has to be a first order effect to cause them. So you have to either be experiencing some sort of velocity, some sort of motion, or you have to be in some sort of insane gravitational field, right? So these lads, Heffel and Keating, are going to go on a mission to measure time dilation using atomic clocks. And what they're going to do is that the gravitational potential of the altitude of the plane, right? They take that as their gravitational equipotential point, and they say that as they move through this gravitational field, with and against Earth rotation, right? But we're all familiar what's really rotating now. As they go through this field with and against it, there's going to be retardation, and they're going to attribute that retardation or gaining time. I'm not sure what's the opposite of retardation, Toby. Instead of retarding time, like what's the so it's just going to gain time essentially, right? So within the relativistic sense, and this is based on the gravitational potential, right, of like how far away you are from the surface of the Earth, right, at that gravitational potential, right? So they take these two clocks, they go around the equator going east, and then they do one going west, and they take their measurements, and we're going to look at the predictions and whatnot, and the measurements. So we have here from their 1971 unpublished paper that had to be FOIA requested by an Irish physicist named A.G. Kelly, which we'll go through the documentations here in a second. But the measurements and everything that they put out, we will look at in a simplified graph form here. So we have the predicted Heffel and Keating amounts here. We have what they actually measured, right? So these are the relativistic predictions. This is what they measured in the experiment. Now, what we found, like as if I was involved, what A.G. Kelly found through the FOIA request, because this was funded by the government, by the Navy, I think. So anyway, he FOIA requested that, and what he found is during the debriefing is that these atomic clocks went out of sync way outside of the parameters of the prediction itself, and they had to correct them like manually and like reset them, like essentially reset them or ignore the just ignore the readings because it would invalidate the experiment. And this happened on, so there was 4 clocks, and it happened on all of them to varying degrees multiple times. And so they ignore that, and then they say let's see if I have it documented. No. So they actually say in the debriefing that they're like, look, man, the difference between theoretical prediction and measurement here is alarming. So this is what they measured before they corrected everything, right? They're not even close to relativistic predictions, and they even say in their own words, they say that the measurement between the difference between experiment and measurement is a disaster. And if you're not already into relativity, this would not really be convincing evidence for the theory. And I agree. So in 1972, luckily though, they republished their, or not republished, they published their corrected values, and wouldn't you know it, they found time dilation.
This didn't look hard enough.
Yeah, and they attributed the causal mechanism to it, to the equipotential of gravitation, right? So so what Earth's gravitational field would be at the surface versus what it would be at however high the plane flies, like was it 30,000 feet, 35,000, something like that. So they take that gravitational potential and they're like, okay, gravitational field confirmed, time dilation. Now, through the equivalence principle and all their mathematics, all right, and back engineering all this, it almost seems like that's a reasonable way to attribute what happened, right? Or did these clocks retard due to relative motion through an ether wind? Right? Because when you get into the corrections, right? Now this is where it gets really crazy. Because we're gonna deviate a little bit from the traditional presentation, and we're gonna look at the atomic clock corrections for GPS. We're gonna look at all the GPS corrections for relativity, and we're gonna see what they are. Shout out to Paul Marmé. So this is really interesting here. We have these corrections that we're told are in relation to gravitational potentials of how far away you're away from the geoid, Earth rotation, relative velocity of the craft, accounting for the Sagnac effect itself, right? But what we notice here, what Marmot tells us, is that all these equations are identical to equation 13, which when we go back to equation 13 is the Sagnac effect, which he points out. So they're literally accounting for relative motion through a field. You would never know if the difference in the correction is due to the Earth's gravitational potential or if it's just due to relative motion through ether wind. It's the math they use to make the correction is the same one. Like, so, and that's really important because in 19, let's see, yeah, right here. In 1995, there was a paper, 1996, there was a paper that came out where engineers that work in GPS were wondering where their relativistic corrections might be. So they said, well, our instruments aren't sensitive enough to account for time dilation and relative velocity through the equipotential gravitational field. So we'll just hang tight on that. We'll implement them later, right? It was essentially their analysis. Now, when the instrumentation got better, how would you tell the difference between accounting for the Sagnac effect to a more precise degree versus accounting for time dilation due to relative simultaneity?
Yeah, especially when they word it the way that they do. It's like, well, we'll find it eventually.
Yep. And then on that,
yeah, go ahead.
Yeah, and on that note, for relative simultaneity, right? So the whole jumping off point for this whole theory, for this whole conception, for this to even be an answer to an experiment like Michelson-Morley, which we'll cover in a little bit, for this to even be viable, something called relativity of simultaneity has to exist. Meaning there's not a cohesive timeline that events can be sank to. Observers will measure different things. Stationary observers and observers in relative motion will make different measurements of events that are happening that are stationary or in motion relative to them, right? So there's this never-ending cascade of relativistic corrections that would have to be made, transformations, etc., right? These are not present in GPS in 1995. And then in 2000, we have the Paul Marmot paper where he's like, hey, they started accounting for this or whatever. or these are the new equations that they're using, and they're classified as one's the gravitational potential correction for general relativity. The other, there's a velocity correction for the Sagnac effect in regards to quote unquote Earth rotation. But they're all the same. They're all accounting for the same thing. And there's no relative simultaneity corrections. There's no transformations required to make measurements and sync events to a cohesive timeline in GPS. So the entire framework on the face of it is null. It's invalidated. If their conceptualized version of how measurements work and why we didn't measure a velocity with Michelson-Morley existed, GPS would work differently. They would have to make specific corrections to the atomic clock, and they would have to make specific adjustments to the measurements after transformation to keep the timeline cohesive. So, super important. And sorry to get off a little bit, but they act like putting planes on clocks and the retardation of the clock or the gaining of time, like so, just like it's the oscillation rate goes faster or slower. So they attribute that to time dilation, and it's like it's not even on the table, guys. There's a first order effect at play that's way outside of the confines of that, and they act like it's the other way around. They act like they can only explain that in a second order equation, but we just looked at the equation that they use for the correction. It's the same. All right, so now we got gravitational waves real quick. So Toby knows quite a bit about gravitational waves, and I think he will thoroughly enjoy this portion of it, but we're not shared with audio. 1 second.
Always good to relive a nice moment in history.
It's always good to relive a nice moment in history. So shout out to the 2015, 2016 LIGO crew who made this amazing measurement of GW 150914. Here we go.
Ladies and gentlemen, we have detected gravitational waves. We did it. Ladies and gentlemen.
Awesome. So earlier when we covered the Kerr metric for two oscillating black holes, their collision, right, would produce a time differential that would cascade out in perpetuity at the rate of c. And if you have a large enough interferometer, perhaps you could measure this temporal displacement rippling through time, which is definitely not absolute, right? It's just cascading through a not absolute time. Dude, what a joke, man. All right, so they got this temporal displacement that's just going through the universe, right, with no cohesive timeline or anything to be traced back to, even though they know exactly when it. Jesus, dude. Okay, so let's talk about what they say they measured here. They have a 4-mile long interferometer, right? Or what is it, 4 kilometers, something like that, or orthogonal setup. And they say that they measured this temporal ripple in time. So they got a little French shift reading, or maybe not. Like, who knows? It's all facilitated by analytics through a convolutional neural network. But for the purpose of this story, what they say that they measured there, what people don't know, is that they also do blind injections where they send fake signals, like they do, false alarm signals to the team, and everyone analyzes the wave. They all think it's real. They get super pumped. They all start investigating it. They start making sure that's real. They start confirming it. They do all their math analysis. They start checking the machines. They make sure they're operating functionally. They start, looking at the convolutional neural network that birthed the reading that said that they got the confirmation. They start going through all of that to make sure that it's real. And what they found was that it's one of the times that they were about to go live, like actually one of the first times that we're aware of anyway, they were about to go live and say that they successfully confirmed gravitational waves. And then it was revealed by probably this guy that said, like, congrats, ladies and gentlemen, we did it, that it was all fake and it was a ruse to see if they were able to detect a fake wave from a real wave. So it turns out that they were not able to do that. Otherwise, they wouldn't have went forward with publishing and a press event and all that, because they had to make these people think that it was real so that they would apply, the maximum amount of scrutiny to it. So anyway, that was the ruse. They can eject blind data. And then there was another story called The Astronomer Who Faked It, which is basically another rendition of this, where a team was given access to their servers or, to their equipment and everything. And then they did, they would just do drills on these people. So when you go to that interview from Veritasium, and that guy that's worked at LIGO for 20 years or whatever has Veritasium's like, hey, aren't you super pumped for this detection? He's like, no, not at all. How many of these do you think that guy went through before he was just like, okay, I don't care. So when you get into black holes and the causal mechanism of them anyway, it's fun because they talk about a singularity, right? And what's a singularity? Well, suppose you have a y-axis and an x-axis, and you have a curved line going down to zero, but it never quite reaching it on the x-axis. So you would just get this infinitesimal convergence that never quite reaches it. This is a singularity. This like unmeasurable, never-ending, can't quite reach it, trending to zero. And they get that through imposing conditions on the metrics that they're using for the math that break the metrics so that they're not able to describe the phenomenon. And once they do that, which is essentially them dividing by zero to create this singularity, they start attributing, mass to it and all that so that they could treat it as a gravitational field, so that they could start using it to explain or provide explanations to phenomenon that they can't explain through normal metrics, right? When they don't have enough mass to explain something, rotating too fast so that it would rip itself apart, or when something's moving too fast around, nothing in the sky, they're like, oh my God, there must be a singularity there, and the mathematics must have collapsed such that it just curves infinitely on itself, and now that somehow has mass that they can attribute to it. So that's singularities and black holes in a nutshell. And then we get into experiments with light, which ended up becoming its own presentation called The History of Interferometry. So definitely check that out. And this is more in regards to the special theory anyway. So we'll kind of just leave this untouched for now, honestly. All right, how are we looking here? So like those are the main proofs, right? So to give a quick recap, right, the important parts of the presentation regarding, I just added gravitational waves at the end for just to nail that home, because that was like the recent thing, right? But the core of this theory, the backbone of it, is the redshift. And then obviously propping it up through the historical narratives of the perihelion precession and the deflection rays. So we learned that the perihelion precession can be explained through, any sort of proportional scaling mathematics, especially when you have the freedom to change the input or boundary conditions of your math equations. You can impose ideal conditions to explain anything, and this is a post-diction, not a prediction, so it doesn't give any sort of special validity to a theory, especially with the aforementioned freedom to swap tensors to explain the phenomenon. And then we learned about deflection of light rays and the story of that. So the deflection that a living man has seen with his own eyes, or woman, only occurs within the solar limb of the sun. So there's no this like far out projection and all this stuff, no one's ever seen it. It only happens in the solar limb of the sun, which, depending on your cosmology, the sun could be made of different things, and there could be different mediums interacting at that area. So those could all cause said displacement. And we also learned about, what was the other thing with that? It just had it, but anyway. So the gravitational redshift would be the substantial meat of how they prop this bad boy up, and that was done in 1960. In the 1960s with Pound Snyder and Pound Rebka, because prior to that, using stellar or solar and celestial observations, they couldn't substantiate gravitational redshift to any degree that would be required for the theory. And there's an entire history regarding the predictions and the meaning of the predictions and the revision of the predictions and the meaning of the revision of the et cetera, right? Until they finally land on pound Repka pound Snyder, which we learned they couldn't tell, like, the predictions for essentially classical mechanics and the relativistic mechanics were the same, right? So they couldn't make any they couldn't tell any difference, and they suggested maybe they do one with atomic clocks so they could see if the speed of light's actually traveling faster. All right. So I think that's everything. If anyone has any questions, comments, or concerns, feel free to ask.
Are there any more observations of gravitational lensing that they would reference since then?
Yes. So there was one in the 80s, I think. There was one in the 2000s. There was one from, I think Dowdy mentions one or cites one. And then you get into papers where it's not something that somebody observed. It's something where they say that they've measured it with XYZ radio telescope. They've mathematically extrapolated that this frequent blah blah blah, that kind of stuff.
So
and then obviously you get and then you get the art from like James Webb Telescope.
So they don't measure it; they compute it.
Yes. Yep. For the stuff that they tell us, yeah. So like when you go here, what's gravitational lensing? So when you see like an Einstein ring like this right here, like no one's ever put their eye through a telescope and seen that, right? No one's ever looked through a telescope and seen anything like this where they're like, oh my God, this light's being bent around the mat like this. No, never. Not once. Or anything like this. No one's ever once seen that. It's all within the solar limb. And they build the whole mythology around that, and they show us these images. And they're like, whoa, an Einstein ring. Einstein confirmed. Look, we found an Einstein ring right where we looked. Right where we were looking for it.
Right where we computed it to be.
Yeah, exactly. Exactly.
Well, cool, man. That was a pretty great rundown.
Thank you. Thank you.
That's their beautiful house of cards that they have built.
Yeah.
So yeah, anyone, any questions, any comments, concerns? Ice cream to throw at us, whatever.
Dude, I'm actually a little disappointed that Shane isn't here to see the 8th rendition of this. Like, I don't even know if he like actually studies the material or not at this point. If he's not here for the 8th one.
Yeah,
like,
right. He must not care.
But yeah, man. So that's general relativity and the historical narrative put forward.
Cool. Well, yeah, so this Thursday, I'm not totally sure what we're going to be reading yet. Possibly something about spectroscopy. But that's subject to change. And also not totally sure what we will be covering next Tuesday. But we will be covering a topic. We will be doing another presentation. But yeah, thanks everyone for tuning in. And if there's no other questions, we can go and wrap it up.
Nope, that's it, I think.
All right. Peace out.